Okay, so we're going to do number 4, which is good. It'll reinforce what we did yesterday in class when we did this almost exact problem. So this will be good reinforcement. All right, so we've got this car and this truck and colliding and traveling off together. So what type of collision would this be? Inelastic, because the two or more objects become a single object afterwards. All right. So let's see. It's going to be number 4. Probably be good to start off with showing that I understand what momentum is. Do I have a system here? Yes. And I think they tell me to ignore friction, right? Let's see. I think they're wanting me to, so we can isolate our system and say the system is just the truck and the car. And that's important because we know momentum is conserved in the system. Right? Do I need diagrams for this one? Yes. I have a system, and I have a before, and I have an after. So, let's see. What was I? Car is coming from the east, moving east. Truck is moving north. Okay, so remember, don't be intimidated by my awesome drawing ability. Momentum of the truck, momentum of the car, they join together and have momentum of the truck car in that direction. And this is my truck car. Is there anything else that I need? Let's see. I think that would be about it for my why. Showing clearly that I understand what a momentum is, that I understand that the two of them together make a system, and that momentum is still conserved in that system. Is kinetic energy conserved in this system? No, only in elastic. So not in this one at all. And then, so I use my momentum of the system being conserved. And that's important because it's vectoral. So what I'm going to do is I'm going to do a diagram here. And we have the momentum of the car, momentum of the truck, and then we have the momentum of the truck car together. And they tell me, let's see, they give me one other piece of information, a couple other information. Let's see. Mine's 45 above the x-axis. So I have 45 degrees here. Oh, I got kind of lucky. Because I know that a 45, 45, 90 triangle has legs that are the same value. So I know for mine that the momentum of the car and the momentum of the truck have the same value. If you're not lucky enough to get 45, in other words, you didn't pay the WebAssign gods enough, then you have to, your trig is a little more tricky. All right? But let's see, let's assume I don't have a 45 and do it. Well, I'm going to use 45, but I'm not going to use that logical jump of mind of knowing those two are equal. Okay? So they want to know the initial speed of the truck and the final speed of the wreckage They tell me the velocity of the speed of the car, the inertia of the car, the inertia of the truck. All right. So I want the inertia. I want to figure out the inertia of the truck, the momentum of the truck. Excuse me. So I'm going to start off by saying that using SOHCAHTOA, so tan of 45 degrees equals opposite momentum of the truck over adjacent momentum of the car. And I can break those down into the inertia of the truck, speed of the truck, over inertia of the car, speed of the car. And I know, let's see, I know the inertia of the truck. I know the inertia of the car. So I can just kind of substitute in things I know. 45 degrees equals, let's see, inertia of the truck. Is that 1500? 1500. I don't know I don't know the speed of the truck, right? 980 and 18.3. I know the inertia of the car, 980 kilograms, and the speed of the car, which is 18.3 meters per second. And a little algebra, and I can find out the speed of the truck. That's a terrible feat. And they want to also know, let's see, they want to know the speed of the wreckage. Okay? So, let's, we can do it with either Pythagoras or with cosine or with sine. I think I'll do it with cosine. So I'm going to do cosine of 45 degrees equals adjacent momentum of the car over hypotenuse momentum of the truck car. And so I'm left with cosine of 45 degrees equals inertia of the car, speed of the car, over the inertia of the truck car, which is the inertia of the truck plus the inertia of the car, and then the speed of the truck car. And then it's just substituting in, right? 980 kilograms, 18.3 meters per second, over 1,500 kilograms, 1,500 kilograms plus 980 kilograms, and velocity of the truck car or the wreckage, however you want to say it. And just have that one variable to solve for. So let me know if you need individual help on that, or if there's any questions on it in general of how I did that. Alright, so do number 5, see where we go from there. Truck, mass is this, moving rear end's this. What does it mean that the collision is elastic? Okay, that can happen with semi-elastic too, but you're right, that's a good thing. Make sure we know. In fact, in this one, where we have this heavy truck hitting a lighter or a less inertia car, is the truck going to move back or keep going forward or stop? It's going to keep going forward. It has more inertia. It has less inertia to move backwards, but the same inertia could stop. Right? Yeah. But what else do we know because it's elastic? Crucial fact, without it we can't do anything. Is conserved in the system. Right, kinetic energy is conserved in the system. So, right here, of course, we want to show that we understand what momentum is, right? That going fast. The car and truck are a system. Oops. Momentum is conserved in a system. Kinetic energy is conserved in systems because it's elastic. And probably be good to show that you know the kinetic energy is energy of motion. A lot of shorthand there, but you get the idea. It's conserved in the system. Yep, because it's elastic. Do we need a diagram? Yeah, because we got a system where we got a before and after. So let's see. That stop. Okay. So we have our truck and our car. Momentum of the car before is 0. Momentum of the truck before would be in that direction. Afterwards, we still have our car and our truck. This is the car, that's the truck, sorry. Car, truck. The truck is still moving in this direction, so it has momentum in that direction. We'll call it momentum prime. And now the car is also moving in this direction. So now the car also has momentum in that direction. So that's what you would, you'd need all of that to get full credit on your Y. Alright? So I'm going to take to the right as positive. I'm going to start off with the fact that momentum of the system is conserved. Before the collision, I have 2 bodies. After the collision, I have 2 bodies. So I need 2 terms before and 2 terms after my equal sign. So I have the momentum of the truck before plus the momentum of the car before equals the momentum of the truck afterwards plus the momentum of the car afterwards. Designating the after by the tick marks, by the prime indication. Now, using that I know what momentum is, I have the inertia of the truck, velocity of the truck, plus the inertia of the momentum of the car before is 0 kilogram meters per second. And then I have the inertia of the truck, velocity of the truck afterwards, plus the inertia of the car, velocity of the car afterwards. If I substitute in what I know at this point, it would become clear that I know everything except VT prime and VC prime, but I'd be kind of stuck. So I could just substitute in all my values that I know. Then I would realize I don't know enough of the values to continue. So I would skip down. I'm just going fast. There's a couple more problems people want to do. I go to my fact that the kinetic energy of the system, is conserved. So it's the same before and after, just like my momentum. I'm going to have 2 terms before because I have 2 bodies and 2 terms afterwards. So I got kinetic energy of the truck plus kinetic energy of the car equals the new kinetic energy of the truck plus the new kinetic energy of the car. Notice that those are scalars, not vectors. So the directionality doesn't matter with kinetic energy, or it does matter with the momentum. So now substituting in, I know the kinetic energy is energy in motion from my equation sheet. I know the equation for it, which is 1/2 inertia of the truck, velocity of the truck squared, plus 1/2 inertia of the car, velocity of the car squared, equals 1/2 inertia of the truck, velocity nu of the truck squared, plus 1/2 inertia of the car, velocity of the car squared. Hopefully, mathematically, you notice there are some things that can cancel out. Things like there's a 1/2 term in every part, so those can all disappear. Also that since VC is 0, VC squared would be 0, and so that whole term, the 1/2 MC VC squared, becomes 0. So you're left with, once you cancel everything out, inertia of the truck, speed of the truck squared equals inertia of the truck, the new speed of the truck squared, plus inertia of the car, the new speed of the car squared, and you end up with the same two unknowns, and so you have, mathematically, you have two equations with the same two unknowns, therefore you can solve it. It's all, physics is all done, it's all math now, so you just have to solve these two equations, which have the same two unknowns, and you can find the V prime T and V prime C that is what it's asking. Alright? I'd suggest using either your calculator or Wolfram or something to do it, or you can just do it algebraically by solving one for the other and substituting in. Alright? But the physics here is that the momentum is conserved in the system and the kinetic energy is conserved in the system, and that is what controls the problem. Any questions or